All right, so first example, we'll look at a rotating bike wheel. So let's say the bike wheel spins around 4 times in 1 second, and we want to describe how fast this thing's rotating. Not just a particle, but every part of the bike wheel, how fast is it going. So we're looking for angular speed. So angular speed, it's a lot like angular velocity. It's the magnitude of the angular velocity vector. It's the size of that omega vector, not taking into account direction. So I need to know how far this thing is rotated in a period of time, basically distance over time to calculate speed, except we're doing this in an angular sense. So the thing's gone through 4 rotations or 4 revolutions. So in the numerator, my delta theta, my angular displacement, is 4 revolutions, but the revolution isn't the right unit for angular displacement. So I have to do a dimensional conversion between revolutions and radians. So 1 revolution is the same thing as 2 pi radians. And by multiplying 4 by 2 pi, I can cancel out the revolutions, and I get 8 pi radians as the angular displacement of the object. And 8 pi then in 1 second is the amount of time it takes to do this. So 8 pi divided by 1 yields 25. My calculator can find that for me. 25 radians per second is the current angular speed, the magnitude of my angular velocity. Okay. So that would be angular speed. And let's see, second part of the question, what is its angular acceleration if it stops? And I don't know, I'm spinning the bike wheel. That thing has very little friction. It will spin for a long time. So let's say, well, I don't know, this might be a little long. Let's say it goes 3.5 minutes before it finally comes to rest and friction brings it to rest. Well, what kind of angular acceleration are we talking about here? So now we're looking for alpha, our average angular acceleration. It's going to be my change in angular velocity, delta omega over delta t. Okay? So this will be my final angular velocity minus my initial, divided by the time interval in which this occurs. Okay. So if it's going to spin to rest, the final angular velocity is going to be 0. My initial is the 25 radians per second. And then the amount of time that it takes to do this is 3.5 minutes. So I got 3.5 minutes, but I also have to be careful again with my dimensions that I have this in seconds instead. So 1 minute is equal to 60 seconds. So what I'm going to do is multiply 3.5 by 60. So we'll take 2.5 radian or 25 radians per second divided by the number of seconds and 3.5 minutes. And my calculator will tell me my angular acceleration is negative 0.12 radians per second squared. So every second that goes by, this thing's going to lose just over 1/10 of a radian per second of speed until finally it stops 3.5 minutes later. I got a negative sign because my acceleration opposes the direction of my angular velocity. By putting 25 radians per second as the angular velocity in, assumes that it was moving in the positive direction, so a negative acceleration, of course, brings it to rest. All right, let's tackle a little more challenging problem that deals with angular displacements and speeds. So let's look at the idea of an eclipse. If the moon is this big distance from the Earth, and the sun is a much bigger distance from the Earth, and has its own radius, which interestingly, the radius of the sun is bigger than the Earth-Moon distance. The sun is a big object. How long is a solar eclipse? We're also given the information of the period of the moon, how long it takes to make one orbit about the Earth in days and in seconds. So let's think about what happens during an eclipse. This is an angular problem, and we'll see how the angle comes into play. So during an eclipse, you, draw a picture here, are watching the moon pass in front of the sun in the case of a solar eclipse. So draw a picture here. Here's the sun, high in the sky like this. And the sun takes up a certain angle. There's an angular size to the sun. So when you look up at it, you see kind of the top edge of the sun, and you see the bottom edge of the sun. And your whole field of vision may be 180 or even 360 degrees if the Earth wasn't in the way. But there's a certain angle taken up by the sun. We'll call that angle theta. And if we know what that angle is, right, the moon is going to be someplace between the sun and us, and the moon is going to have to pass through that angle, and we need to know how long it's going to take the moon to travel through that angle. So we're going to look at a relationship between distance and angular size, or arc length. So we've got actually two arc lengths here. We've got the arc length of the moon as it travels across angle theta. And then we have the arc length of the sun up here, which is, I don't know, this is pretty close to a straight line. In fact, effectively, this is the diameter of the sun. So this arc length of the sun, we'll call that SS. Okay. Then we have two different radii as well. So in the case of the sun, we're looking at this entire distance here. So RS is how far the Earth is from the sun, 1.5 times 10 to the 11th meters. And Rm, which is the distance from us to the moon, which is 3.85 times 10 to the 8th meters. But both of them, in this picture, we got the same angle that matters to me here. So my first step is going to be to solve for this angle. Look at the relationship between angular size and linear size. So arc length is equal to a radius times an angle. So let's do that for the sun. Because we're also given the radius of the sun, we basically have an idea of what SS is going to be. It's going to be double the radius of the sun. And let's use that as our S in this case. So we'll do S for the sun, R for the sun, and then theta. We'll be able to find theta in this picture. So in this case, S of the sun is going to be 2 times the sun's radius. So it's the diameter of the sun. Let's see, the sun's radius 6.96 times 10 to the 8th meters. My radius, distance from the sun, is 1.5 times 10 to the 11th meters. And so then that leaves me with theta. We can figure out what angle the moon is going to have to move through in order to make this eclipse. And it's actually a really small angle. The calculator says 0.00928 radians. And so that's the angular size of the sun, and the moon's going to have to travel through that angle. So we need to know what the moon's angular speed is in order to figure out how long it takes to travel through the said angle. So let's consider the moon now. So we looked at the sun for the first part. Now let's consider the moon. And let's think about its angular velocity, the rate at which it moves through angles. Okay. Now, we have no idea how long it takes to go through this particular angle, but we do know how long it takes to go through an entire rotation. So we can use that to find our rate. So let's let it go through an entire rotation, which would be 2 pi radians. And we're told that that takes 2.36 times 10 to the 6 seconds, or just over 2 million seconds to go once around the circle. So now we can get the rate at which the moon is moving as an angular speed. My calculator says 2.66 times 10 to the negative 6 radians per second. Okay, so it has a relatively low angular speed. But now that I know that rate, that particular angular speed, I can go back to my angular speed equation and this time solve for the amount of time that it takes to move through this angle. So omega 2.66 times 10 to the negative 6 radians per second is equal to, we want it to travel through a displacement of 0.00928 radians. So that leaves delta t as my unknown variable. We can figure out how long it's going to take for this to occur. And if I use my calculator to solve for this, delta t is equal to 3,490 seconds. So almost 3,500 seconds, which comes out to be 54 minutes. So we're going to expect a solar eclipse to be just under an hour. Our predicted value for the time it takes the moon to pass through the angle is just under an hour. Now here's the funny thing. If we go online and we look up the time of a solar eclipse, we find that the actual time for a solar eclipse is double that. It's about 1.9 hours. So we get almost, we're off by a factor of 2. And to understand why that is, we've got to go back to our picture here and think about what we just solved for. We solved for the time it took the moon to move through angle theta. But really all that we've allowed it to do, we've allowed the front edge of the moon, this point right here, to travel an angle theta and move to this location here. So after 54 minutes, the moon is now in this position. So actually we've solved for the time to totality. And it's going to take another 54 minutes for the back edge of the moon to travel through the angle theta as well. Interestingly, the sun and the moon have almost exactly the same angular size, which is why eclipses look so neat. The moon isn't making just a tiny black circle on the face of the sun, but it just about completely covers it up. And that's actually coincidental because they're very different distances and sizes, but they take up the same angle of the sky.